I'm setting everything up. Yeah, I know. I'm bored too. Everybody is. Oh, hi, buddy. Alright. Yeah, hi. Hey. So, he's sitting on a stool next to me. He likes to hang out with me while I do stuff. Mainly because he gets rubs. Return of the Johnson. Oh, no. Neighborhood watching? He's gotta watch the neighborhood. Alright. You're not crazy to think it's due Friday. It is due Friday. The way it works is it's due tomorrow, but you get your 3 late days for free. So it's due on Friday. But don't try to turn it in late on Saturday or you will get no credit. So, do you have anything to add to that? Okay. So effectively it's due Friday. Yep, you have till Friday. Yep. It's been that way for a week-ish, I think. That's why I delayed talking about the Splay trees until today. Would have been a little late if the project were due tomorrow. Don't you get on this table. Okay. Nice. Alright. Are we ready to teach? Buddy? Hey. Yeah. Are we ready to teach? Oh, yeah. Alright. Here we go. It's going to be a relaxed day. We're kind of ahead of schedule on the lecture schedule. So that's good. So we'll spend some time on the project. But first, we're going to go over heaps again. Just go over some more heaps. You guys were a little about leftist heaps. So we're going to go over some more leftist heap examples. Oh no, I can hear myself. No one wants to hear that. Especially you guys. Not twice. Not twice. Alright. Alright, cool. So let's go over to Photoshop. I know you probably want me to go over to the project. Oh, Photoshop. I know you probably want me to go over the project first, but oh well. We're doing this. We're doing this, guys. Alright, cool. Alright. Great. So, last time we talked about leftist heaps. And I'm down here in this corner. So we have balanced binary search trees. So this is the superpower column. So like, why do we use them? So the superpower for BST is we can get sorted priorities. And we can do this with, we can do all of these operations with all of the different heaps. It's just that the superpower one is the one it's like the specialization of that data structure. It's the thing that it's the operation that it performs efficiently. So the max heap, which is the array-based heap, that performs construct quickly. And then we're talking about today, as we talked about last time, leftist heaps, which merge efficiently. Okay? So those are the superpowers, like tablify here. So those are the superpowers. So again, on your next exam and on the final exam, there's going to be word problems where basically you're given some kind of programming task, and then the question is, what data structure will efficiently store the data required for that task? So, you might be given a priority queue problem or a problem that could be framed as a priority queue, and the efficient answer is you might pick any one of these three and you'll get partial credit, but there'll probably be one I have in mind because I'll be looking for a priority queue that can be merged efficiently with another one, or that I can get everybody out, and so I could get like the third most high priority person if I wanted to, or so on and so forth, right? So the point, one of the takeaways from data structures is, like I said earlier in the semester, is it's kind of like we're building a roster of fighting game characters, and each one of the data structures has a thing that it's good at, like it's efficient at. And so that's one of the takeaways I want you to have from this class is, if you're going to go implement something, knowing which data structures are going to perform efficiently. That's sort of one of the goals of the class, aside from really getting you more comfortable with more advanced programming challenges, like the ones we have for Project 3. All right, so we talked about this merge operation. We're going to say that the merge operation is big O of log n. And we won't go over the proof for that, but we'll say that the merge operation is big O of log of n. So then, remember, how do we do insert? How does insert work? So think about that while I draw a heap that we're going to insert into. So let's make this a max heap this time. We'll put 59 at the top, and then 38, 1, 17, and 8. Question is, how does an insert work while I'm doing this? Think about that. It's been a few days. I've lost my tablet chops. I'm giving this pen like a death grip. Am I not getting the chat updates on my phone? Oh yeah, I'm not. Phone. Let me fix this real quick so I can see what you guys are chatting up on the chattables. What did you miss? You missed Jules and I had a conversation. Are you leaving? Class is not out of... Alright. You didn't miss much. We're just talking about all the data structures and what their relative strengths are. Okay, so how does insert work? First of all, is this a leftist heap? Well, it doesn't follow the heap order property because 8 is below 7. Oops. So I'm going to go delete. Whoops. Oh no, I don't want to get rid of these lines. What? We'll make this 3. Wow, that is a gnarlacious 3. 3. All right, so it's a max heap because every node has children that are less than it. And is it a leftist heap though? So our leftist heap property looks at null path length, which is how many hops. Each node's null path length is how many hops it takes to get to a null pointer. So from here, this is a leaf, so this one's got a 0. This one has a null pointer here on the right, so that's a 0. This one has a null pointer here on the right, that's a 0. This one has 2 null pointers, so this one's a 0. This one has 2 null pointers, so this one's a 0. And then this one has to hop either to 22 or 19 to get to a null pointer, so it has a 1. And so this one has to hop to, if it was trying to get there quickly, it would go through 21, so it's 1. And so if we look at this tree, all that we need for a leftist heap is that the null path length on the right is lower than the null path length on the left. could I add a child to 19 and still have a... could I add a left child to 19 and still have a leftist heap? Could I give 19 like a 2? Is this still a leftist heap with that 2 there? And then we're still thinking about how do I insert into this. So we're going to insert. Let's insert 18 in here. So how does 18 get put in there? So, is it still it actually is still a leftist heap if you put this 2 in here, because this has a 0. This 19 still has a null pointer right next to it. Oh, so you're talking about complete. Well, it certainly wasn't complete before. We only care for max heaps when they're implemented with an array. We only care about completeness there. Here we care, does it have the heap order property, meaning each node is either greater than or less than all of its children, and that has to. So if it's a max heap, a node has to be greater than all of its children, and if it's a min heap, it has to be less than all of its children. So we have that one property. So that's the one, the heap property. All of these tree heaps have to have the heap property. And then the second is what makes it a oh gosh, this pen has buttons on it that I need to disable. Is what makes it leftist, and that cares about null path length. You're not big dumb. You had the right answer for the wrong heap. It's okay. It's close. Okay, cool. So, how do we insert? Well, we could try to come up with some fancy algorithm, blah, 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 but we have this big crazy merge over here. So what we're going to do is we're just going to say, well, we have 2 heaps. One contains all this junk on the left, H1, and then one contains all this junk on the right, H2. But all this junk is just 18. So, I'm going to erase insert here. Can I make this brush size, like, not the tiniest? Yeah. Oh, yeah. Okay. I'm getting better at this. Okay. So we're saying that H1 over here is going to be 59, and H2 over here is going to be 18. Okay? So that's our insert. So these are node pointers to individual nodes. So one is pointing to 59 and the other is pointing to 18. And so we're going to do an insertion. So the only thing that actually goes on in this main function is it's figuring out which one of H1 and H2 is greater and which one's less. And so it's basically just calling merge 1 such that H1 is the smaller of the two, which will be 18. And then H2 will be 59. If H1 left is null, H1 left equals H2. And so we'll just make my left pointer 59 and this one null, and we're done. That's it. Done. And so what's the null path length of 18? Why, it's 0. We're done. That was easy. So if you're... Wait, how could that be true? Oh! I have it backwards. This is a leftist heap. It's like, wait, this can't be right. I made a max heap, and this is a leftist heap for a min heap. No. What? Yeah, you're correct to say what. This is... So if I had inserted, Oh boy, now I have to turn this heap upside down. Well, let's just make a new heap from the start. We have to use, this is a min heap on the left. This is the leftist heap code for a min heap. So we would have to, for the sake of not having to swap-a-roodle all the so we don't have to swap all the left-hand sides and the right-hand sides. We're just going to start over. Okay, so I'm going to start a new, we're going to do a min heap this time. So I'm going to start it with 15 as the first value in the min heap. Then we're going to insert 17. So it goes in, this will be H1 into merge 2 because it's the smaller number. And then it's going to say, okay, is H1 left null? Then make H2 it. So, boop, we're going to have 17 in here. Can we maybe go back 1,000 steps? Yeah, we're going back 1,000 steps. Yeah, let's go back to 202. Okay. We need guidance. Okay. So we're just doing a mid heap. I had the heap upside out. I'm sorry. I know that was super confusing. Apologies. The min heap was upside down. We need to use a min heap, not a max heap, for this code to work. Okay. I'm going to insert 20. So now we're going in here. We have 15 and 20. Since 15 is less than 20, this gets called with 15 and 20. And I'm going to pause. We're going to do this one really slow. So that if anyone is confused about why merge 1 is called with 15 and 20, throw up a hand. Okay, so merge 1 is always called with the H1 being the lesser of the two things that we're dealing with, the two roots that we're dealing with. Thank you all for collectively freaking out. That lets me know I need to like start over. Okay. All right. I'm assuming we're all good on why. I'm even going to look at. Oh, okay. We need guidance. Throwing up a hand. Okay. I'm assuming you guys are okay with merge 1. All the main merge does is it looks at the two roots and it says which value is smaller. I'm going to call merge 1 with the smaller value being H1 and the larger value being H2. This is a min heap. This is a min leftist heap. Min leftist heap now. And we're putting 20 into the min leftist heap that is 15 and 17. Okay. So now we look, and so H1 is 15 over here. I'm going to get rid of these labels because they will confuse us eventually. All right. So right now we have in merge 1, we have this is H1 and this is H2. Okay. So we're saying if H1 left equals null. It does not. So we have to go down here to the right. Then H1's right equals, H1's right is going to equal the result of merging H1's right and H2. So we're merging now up here, we're merging null pointer and 20. And then we look in this code, if one of them's a null pointer, we just return the other one. So the result of merging null pointer and 20, so we're done with this one now. The result of merging null pointer and 20 will be returning 20 over here to this part of the recursion. So this thing returns 20. And so now we're saying 15's right node is 20. So our resultant merged situation is this. And I will... What makes it leftist again? It will vote for Bernie. What makes it leftist is the null path length has to always be greater, equal to, or greater in the left child of any given node. And the null path length is how many hops it takes to get from that node to a null pointer. Also, if these two things have a difference in null path length, so we have to run this line of code, then we swap them. But we're not going to swap them because they have the same null path length of 0. So we have 0, 0, and 1 for our null path lengths. Is the left node an 11 or a 17? Doesn't super matter, but we'll say it's a 17. Okay. Any questions about what I did? I think you're all aboard on this. Can I get some thumbs ups? Or, I don't know, some stuff? Jules, what are you sitting in the corner for? Give me some thumbs up. This is so much harder to teach online. It's hard to teach in class, actually. This was sort of the lecture I was dreading. It gets better from here. Oh my. All right. Thumbs ups. Good. I think that's a... Is that a dabbing emoji? All right. I'm going to start going a little more, and we're going to see how this goes. And then we're going to do splay trees, and then you guys are going to have a very confusing 341. Jeremy has doubt. I'm assuming that's Jeremy. Okay, people are good. Yeah. Awesome. Okay. So now, let's insert a value. All right, let's put in 12. Try it before I do it. So we're going to insert 12. So we're just doing the merge on these two things. Try it out while I erase it and see what you get. It's a bit easier to understand, and oh no, I'm deleting the algorithm too. Whoops. Need to be more precise. If I were better at dealing with layers in Photoshop. Well, no, actually, I wouldn't be able to draw on the code if it were. So how does this work? Tis he. All right. How do we do 12? So, first thing we're going to do, we look at the key values of the two roots, and we determine for merge 1, what is the smaller of the two. And the smaller of the two will be H1 in the merge 1 recursion. So the smaller of the two here is 12. So that makes 12 H1 down here. And 15 is H2. Okay? So now we're saying if H1 left is equal to null. Okay, so 12 is H1 and its left is in fact null. Then all I'm gonna do is just make H1's left equal to H2. Oh, okay. Well, that's fine. And my null path length will still be 0 because 12 will still have a right child that's null. And then we're done. So if you're ever inserting into a leftist heap a value that's lower than the root of the current leftist heap, it's real fast. It is real real fast. Because you're just making the new root, and the whole existing heap becomes the left-hand side. Which makes sense, right? That's an easy way of maintaining the leftist property, is to just move everything to the left. So we're not going to do inserts of that type anymore. But you should also think about it, because that's how merge works, if when I'm doing the merge recursively, I'm inserting a single node into something that's greater than it, then I'm going to be done soon. If that makes any sense. All right. Let's put in... Let's put in 21. Whoa, that is a big circle. Whatever. Anyone still lost? Conceptually, it's a cakewalk. Code-wise, it's a nightmare. I mean, this isn't a whole lot of code, but it's complicated, right? Swap children is just a simple swap. Everything else, what you see is what you get here. So, I'm gonna work this one more example, and then I'm actually just gonna go through the code and try to explain specifically why each line does what it does. Okay. Bye. Okay, we're thumbs up in. All right. So we're good thus far. Awesome. So 21. So we look at this. 12 is the lower one. So when we call merge 1, 12 will be H1, 21 will be H2. Then I look here. Is H1's left null? Nah, it's 15. So we go down here. H1's right equals the result of merging H2 with 12's current right. So what will happen here is that then we're going to go up here and we're going to call this with, so the left is 15, oh no wait. We're going to call it with H1's right, which is null pointer. And then we're going to call it with 21. And this will again return 21. So what we'll get here at the end is (21) goes here. It has a 0, and then this one has a 1. We start with merge, and then we go to merge 1. The only thing merge just does, if one of them's null, then that's easy. Merging something with nothing means just return the something. That's what these two lines do. So merge node with null. Just return the node. So I'm just going to go over the code. Then this one is call merge 1 with H1 as smaller key. So that's all merge 1 does. Or that's all merge does. Is it, if one of them's null, it returns the other one, and then it just calls merge 1 such that the lower element is the first item called in merge 1. All right, let's talk about what the heck merge 1 is doing. So the first part of merge 1, this little thing here, what this is doing is it's saying if the smaller thing, which I want to be kind of like the new root, because we're a min heap. If the smaller thing can put something on the left, do it, and then you're done. So if we saw that when we inserted 12, when we inserted this 12 here into this, we actually just made it the new root and then made the whole other subtree its left-hand child. That's the purpose of that little if statement there. Is like if the smaller of the two nodes can just put something on its left, we're happy, we're done, and we'll just be done. So this is like and finish. Otherwise, if we can't do that, then we're going to take the smaller thing. It still needs to be the root, right? H1 is going to be the root in either of these cases. But the thing is, if we can't just immediately put it on our left, we're going to have to put it on our right. But if we have something on our right, we have to merge it with... If we put something on our right, we have to merge it with whatever we currently have on our right. So let's look at it this way. H1 is going to have a left subtree, and it's going to have a right subtree. So, and then there's just H2. What we would like to do is, if the left subtree is null, we just put H2 there immediately and then we're done. So if there's nothing there, we just put H2 there and we're done. Otherwise, what we want to do is we want to make H1 now point to the result of merging these two things. So we want to merge these and make that H1's new right subtree. Okay. So our recursion is, if there's a spot on the left, put H2 there. If there's not a spot on the left, merge whatever I have on the right with H2 and make that my new right subtree. Because H1 has to be the new root, because it's the smaller of the two values. Okay? And so... what else do I want to say at this point? Oh, when I'm done this merge process, I'll swap my two children if they violate the leftist heap property. So if the null path length on the left is less than the one on the right, be like, oh, that sucks, and I'll just swap them. It's like, oh, okay, it's a really easy fix. We're used to these really convoluted fixes for like heights and stuff like that. But if you have a null path length that's greater on the right, then you swap it with the left, and now you're fixed. And then after that, you're just updating your own null path length. You know the smaller one is on the right, so you do the smaller one plus one. Can we start inserting one now? Yeah. Let's start inserting another one. But I wanted to kind of intuitively motivate the recursion. It's really easy to fall into the trap of like, I'm just going to follow the procedure. But sometimes having an understanding of like what it's trying to do will make actually practicing it a bit easier. What it's trying to do is if I'm merging two heaps, it's trying to make the one that has the smaller root the new root, and then it has to figure out what goes underneath that new root. And the thing is, sometimes it has to recurse. All right, let me think of a value here that will cause something interesting to happen. All right, let's do 13. Let's insert 13. So what happens here, right? Let's talk about it intuitively at first. Well, who's going to be the root in the resulted once we merge? 12 is going to be the root, right? Because it's smaller than 13. Well, where would 12 try to fit 13? Well, if it has an open spot on the left, it'll just put 13 there, but it doesn't have one. So what it's going to end up doing is it's going to merge 13 and 21. So then that merge will be a merge of the two trees 13 and 21. Well, what's going to be the root of that? 13. And then how is it going to fit 21 in underneath of that root? Well, because 13 has a left child, it's going to be its left child. Since 13 has a null pointer on the left, it'll just slot 21 in there. But do try to work this out a little bit. And we'll see a little bit of how the recursion works here. And I'm going to clean this up a little bit while you guys think about it. If you have questions, pop them in there. If you're super duper lost and want to see something I already did before, pop that in there. Just, it takes practice and like really trying to sit there and digest what the code's trying to do. But I think we might get there. I'm going to do this for another 10-ish minutes. And then we'll move on. Okay. All right. So what does the normal merge do? What the normal merge does is it just, if one of them's null, it returns the other one, and then it calls merge one with the smaller of the two being h1. So we're going to call merge one with 12 and 13 as h1 and h2. Ooh, I saw something. Why would 13 go on the right and not the left? Awesome question. Why is 13 going on the right and not the left? Well, we'll just follow the logic of the code, right? So, if the left child of 12 is null, then we want to just slot h2 into the left child of 12. Now, Jeremy has an awesome question here. Why not always put it on the left? Will I give you the algorithm for... Yeah, I'll give you the algorithm for Leftist heaps on an exam. You don't have to memorize how to do this. It's hard enough to follow the recursion. Right. So if somebody can answer this question, it's efficiency. So if you're kind of like, oh, I get this is fine. How do I answer this question? Why don't we always just put it on the left? There's an efficiency reason we try to put it on the right. So we can't put it on the left. So what we're going to do is we're going to replace, so remember h1 is 12 on this line of code here. So 12's right-hand child is going to be the result of merging 12's current right-hand child with h2, which is 13. So up here, we're going to come back and we're going to have 21 and 13, which means, so now this recursion is waiting. This recursion is waiting. And now we come down here and we have 13 and 21. Whoops. 13 and 21. So now 13's left child is null, so I can put 21 underneath of it. And I can get rid of 21 here. And then these will both have 0. And then, so now this is finished because we did the first clause here. So we're returning 13 back to this merge. So this is now resolved to be 13. So now 12's right child is going to be 13. Because this recursion is over, we're back now into this recursion between 12 and 13. It's merged. Now I look, if the left hand's null path length is less than the right hand's, we swap them. Well, the left side has a null path length of 1, and the right side has a null path length of 0, so we're done with that. I update my null path length to be the right hand side plus 1, so 0 plus 1 is 1, and then I'm done. Yeah, I've decided the next the next exam is going to be a take-home exam. I won't use a lockdown browser or any of that stuff. The next exam, however, will be significantly harder than the first exam. So the first exam you guys blew out of the water, which is really exciting and great. But for the next exam, it's going to be harder because trees are involved. So there's just so much more on the table for me to ask questions about. So generally scores go down on the second exam, but it'll be a 21 or 2. It's supposed to be a 21. 21. Also, it'll be a take-home exam. So what I'm going to do is I'm going to release it, and you guys will have, depending on how the exam comes out, it'll be a 24 to 48 hour long exam, and it's going to have more coding than the usual exam, simply because it's going to be open book, because I can't prevent you from using like your book and stuff like that. So it'll be open book, and it'll be more coding than usual and more word problems, and it'll be honor code, so don't cheat. I will be checking for duplicate answers and things like that, but yeah, it'll be a take-home exam. How would you swap 13 to make 21 the child of 13? Swap children doesn't mess with... Swap children only swaps the left and right children. So it just takes the left... It performs a swap operation on the left and right children. So temp equals left, left equals right, right equals temp. Could someone explain why it would always be on the left? So why do we merge with the right? Okay, so let's address this question down here. Why we always put it on the left? So if we don't find a spot on the left, why do we go to the right? Like, so the other thing is, why do we go right? So the reason we go to the right is, if we look at this tree, what does the null path length mean? The null path length means how many hops, how many more recursions am I going to have to do before I find a spot to put this damn thing, right? Because if a node has a null pointer, that means it can house the other heap inside of it. So the null path length is a measure of how many recursions you're going to need to make to find a spot for the other tree. And so which child, if I have a leftist heap that's like fully specified, if I have like a big leftist heap, which way am I going to go? Which way am I going to go to find a null pointer faster? Am I going to go to the right, or am I going to go to the left to find a place to actually put the thing? I'm going to go to the right, because the right, by definition, has the lower null path length, which is why, if there's a spot on the left, we say, cool, put it there, just put it there, because I know I'm not going to violate my leftist heap property by just putting it there. And then if there's a, if not, go recurse to the right, because you're not going to have to recurse as much to the right to actually find a spot. So this first clause here is like, did we find a spot on the left? We put it there. Even if my right child is a null pointer, that means my recursion is going to end really quickly. So the thing is, if there's a spot on the left, take it. Otherwise, recurse to the right, because the right hand side is going to have to recurse less. So the answer to this is right hand recursion won't have to go as far. Because that's the whole reason we're making the heap. It's that whole kidney shaped thing, right? So if I have a vaguely like kidney shaped tree, and I have another vaguely kidney shaped tree, and I'm trying to find a place to insert one into the other to merge them together, I'm gonna always go to the right in these trees to find the space for cuddling to happen. So this is the like cuddle recursion, where it's where you're going to go look for the spot where you can perform this cuddling operation. Let's see what everybody said. Yeah, Ezekiel got it, right? We recurse to the right because it's a leftist heap. If it were a rightist heap, we would recurse to the left, because the purpose of the recursion here is to find a spot to perform the merge operation at. So, really good. If that makes sense to you, you're in a pretty good spot as far as like understanding how leftist heaps work. 100% though, for an exam, I'm gonna be expecting you to take two heaps and merge them according to this algorithm, which I will supply. And if it's a take-home exam, so if I don't supply it, I will say, you can go consult it here. And go look at it to save, space. The benefit of using a leftist heap, so each of the three heaps have a superpower. Balanced binary search trees, its superpower is it can efficiently, in n time, print out all of the priorities of the things in the priority queue in sorted order. So, balanced binary search trees are fast for that. Cool. For printing out sorted priorities. This is what I have here in the bottom left-hand corner. Where's my pen? Oh, I have my pen upside down. Jeez. This is when it happens when Jules isn't here to keep me honest. Max heaps, or like the array-based heaps, where they were complete binary trees, those construct very quickly. So if I have a bunch of items sitting around with priorities associated with them and I want to turn them into a priority queue, I can do that really efficiently with a max heap. And sometimes that happens with like in web crawling and state space search, where you sort of assign a bunch of priorities at once, and so you want to create a priority queue efficiently from that set of things. So construct is in O of n for a max heap. Printing out things are in O of n for a balanced binary search tree. And for leftist heaps, we can perform a merge in log n time, which is wicked fast. How in the code did 13 go between 12 and 21? So we were inserting 13. So our initial thing was 12 and 13 right here. And then I said, well, I want to look at the right child of 12, which was formerly 21. So when this was called, when the recursive call was made, it was made with the right child of 12, 21, and the H2, which was 13. So, and then those got put in ascending order for the next merge one call, so it became 13 and 21. So 12 became 21 because its 12's right child was formerly 21. I picked the numbers poorly there. I should have made it like 38 or something. But yeah. Hopefully that answers your question, Anwar. I want to pause if anyone has any other questions. Okay. This was an exam question in the past. I'm not going to give it an exam question now because I'm just going to tell you. If I give you a priority queue that's implemented with one of these heap structures, either a balanced binary search tree, a max heap, a leftist heap. If I give you one of those, and it's empty, and I give you a unsorted array of stuff, how do you sort that unsorted array of stuff using just the priority queue, and how long does it take asymptotically? And Anwar, if you could give me a thumbs up if I answered your question, that'd be great. I'm going to go to a new page here. Create. You have 1 unsorted vector and a priority queue that is efficient. You can pick one, so pick one. I'll tell you now, it doesn't really matter which one you pick. You have an efficient priority queue implementation. Sort the vector. Tell me how fast it is. This was an exam question. This was an in-class exam question. I'll be giving you something longer and a bit more tricky. Not tricky, longer and a bit more harder. We'll just say harder. It'll be a longer question. It'll take you longer to do and be harder, but this is an example of an exam question. This is why I'm telling you the exams get harder. You have an unsorted vector of items. You have a priority queue implementation that's efficient. You can pick your favorite. Just tell me which one. How do you sort that vector and how fast? And I want it to be fast. So make it fast as you can go. All right, cool. Anwar got it. I'm glad. I think you asked that question earlier, and I didn't answer it well. 12 gets connected to 13 via some recursion jank. Yeah, because what the code said was 12's right child becomes the result of merging 13 and 21, and 13 has to be the root of the two nodes being merged, 13 and 21. So then 12's right child becomes 13 in that case. That's how they got connected. Because the H in merge 1, the right child of H1 becomes the result of merging H1's current right child and H2. So that's the recursion jank of which you speak. Log n, you can't do it in log n. This is called a comparison sort. You can prove that a comparison sort can be no faster than n log n. And the answer is much simpler than you might imagine. It's not complicated, but it is something you might have to think about. So we're just sorting a list of values, but you can use a priority queue. An efficient priority queue implementation. And then we're going to talk about scanners. Okay. What's the correct answer is kind of the dumb answer. So what happens if I put something in a priority queue? Well, which priority queue should I use if I want it in ascending order? Do I want a max heap or a min heap? It doesn't ultimately matter, but it makes our code a lot simpler if we use a min heap, right? So here's my algorithm. My answer. Here's your answer right here. 1 in queue the vector values, 2 dequeue them. That's it. Done. Dequeue them like into a new vector. Just dequeue them into a vector. Right? So if I enqueue, because it's easy when we're dealing with leftist heaps and all this stuff to forget what a priority queue is. A priority queue is you put stuff in and it gives you the thing with the highest or the lowest key value. So I'm going to put all these unsorted values into a minimum priority queue, which I can implement. Choose any 3 of our superheroes because we don't actually care. I would probably choose the normal min heap, the one that uses a complete tree. Why? Because I care about construct. Because I'm going to construct the min heap from like a vector, and I know I can do that in on time here. The thing is, I could use any of them because at worst case they all take n log n, and I won't actually upset my overall runtime, but it would be faster to use a min heap because it constructs faster. DQ is not a constant time of 1. Why? So when I dequeue something from a leftist heap, I remove the top value and then I merge the 2 subtrees, which merges log n. So for a leftist heap, dequeue is log n. For a max heap, or like the array-based heap, I remove the top element, grab the last element from the array, put it at the top, and trickle it down, which is in worst case log time. And for a balanced binary search tree, I remove the lowest element, which will take me log n to find, because the lowest element will be somewhere down in the left subtree of the balanced binary search tree. So all 3 of our priority queue implementations dequeue in log n time. So dequeuing all the values in a priority queue implementation is going to be doing dequeue n times, and dequeue is log n times. So that's where we get our efficiency. And that's it. It's actually a pretty straightforward answer. You just load up the priority queue and then pull everything out, and they'll come out in sorted order. You're done. And that's in log n. And this is actually a optimal performance sort, which is hilarious. There's like quick sort and merge sort and all these other like crazy elaborate sorts. Here we're just like, oh, I have an efficient priority queue. Done. It's really easy. Yeah. Heap, and this is called a heap sort. So if you look this up online, I'm not making it up. It's called a heap sort because you use a heap generally. It makes sense to use just a normal min heap because you can construct an n time. So it's, if you enqueue all the values, you could actually, so I should say down here, or construct. So if we want to speak specifically, this takes n plus n log n time. But we dropped this term. Yeah, we dropped this term, but the reason we use those like array-based heaps is because this becomes a lower order term. Instead of 2n log n, it's n plus n log n. So technically, yeah, it doesn't matter what heap we use, but if we use the normal array-based heap, we get a little bit better performance. It's not asymptotically better, but it is better. Yeah, it's log n. So step 2 is n log n, because you're doing log n operations n times. Can you work this out with a sample unsorted vector? No, because I want to get to the project. There's not a traditional dance to illustrate this, like all of the sorts in 201. You actually could heapify a vector with a fun dance, because it would be like me and the person I'm dancing next to looks at the person whose index is half of the next person next to me, and then the three of us dance, and then whoever has the smallest value gets to go up towards the front of the line, and then you repeat that process with their neighbor and somebody up, and then yeah, you could heapify, and then at the end they all just dance out in, and then you just like, you know, you could do it. It would be a really long dance, but it would be pretty efficient. So maybe there's a heap sort one. I don't know. All right, let's talk about scanners. The time has come. Oh, Evan found it. There you go. Oh, so those of you who did not take 201 here, a proud tradition in 201 is when we talk about sorting in 201, we show videos of it's Hungarian folk dance, but they're doing, and it's a lot of like heel slapping and clapping and and we show it for a lot of the basic sorts, so you can visualize. And then the comparison operations are them like kind of locking arms and going la 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 la. The quick sort one has like a hat. They're all passing around a hat. It's very fun. You know when we get Project 1 and 2 grades back? Project 1 grades are coming back very soon. Project 2 prelims just came out today. So, Project 1 grades will come back very soon. Oh, other sections already got them. Yeah, I'll get it to you soon. I've spent my morning working on the Discord bot. So we can make office hours and have shorter wait times, hopefully. Okay. That to me was a bit of a priority. Anyway, all right, let's talk about it. Project 3. Project 3. Da, 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 da. Okay, so you're given a file with some characters in it, with some weights, right? Whoa, no. You're given right, and then it's got a bunch of lines like this. And so you're given the dimensions of this file, height by width, or you can determine it from the file. So there are height many lines, and the lines are, there are h many lines, and the lines are w long. Okay, and so in h by w, that means that there are h times w many characters, or let's say n. There are n many characters. The weights in that file range from 1 to n. And I don't remember how to do the close, 1 and n inclusively. Okay, so there's a file called weights where each of these is some integer value that's they're comma separated. So this could be 23, 49, 18, whatever, in this line, and it's a whole file of them. What we are guaranteeing is that all of the weights from 1 to n are included in that file. About to find out we failed all of the projects. No, it's okay. It'll be fine. The grades will come out probably later today. I just have to do some spreadsheet magic and then put it in the Blackboard. You know, putting it in the Blackboard takes like most of the time. Like, wouldn't it be nice if Blackboard didn't take all the time? If it was just a matter of me doing something sensible? Anybody who's a TA, like Anwar, can vouch. Putting grades in the Blackboard is a menace. I'm not going to do it manually, but doing it automatically isn't much faster. Anyway, so we have the weights from 1 to n. So what we're going to do is we're going to have a tree, and so we're going to have h many nodes. There's going to be h many nodes in the tree, and each node, and we're going to call these S nodes for scanner nodes. Each node is responsible for a line. So if there's 4 lines, I'll have, okay, let's pick some values here. Let's say h is 4 and each line has 5. So I'm going to have a bunch of nodes. One of them is going to be responsible for 1, 2, 3, 4, 5. And then one of the nodes is going to be responsible for 6, 7, 8, 9, 10. And then one of them is going to be responsible for 11 through 15. And one of them is going to be responsible for 16 through 20. Okay? So if I have like an image that has 4 lines and 5 characters per line, we know that the weights 1 through 20 will be in there. So what we're going to do is we're going to make a node for each line of the resulting output, and then put 1 through 5 in one node, 6 through 10 in another node, 11 through 15 in another node, and 16 through 20 in another node. I'm going to... Blackboard UI is non-functional. Swear to God. Thank you. You should make another bot. I'm still working on the bot right now. And I have a backlog. You can go online on GitHub. The newest feature you guys will be able to see, I think will be, you can see where you are in the queue. I might even make it so there's a website for the queue. But for now, the website is actually not so bad to do. The problem with the website is how do I show the queue information without like publishing sensitive student information? So I don't know. It's going to be fancy. Well, actually, it's not going to be fancy. It's going to be weird and janky, but whatever I come up with. Anyway, so we're going to represent each of these ranges by the first value in that range. So in the actual code that you're writing, there will be a pair of values that represent the lower and upper bounds of a particular line, of the weights for that line. I'm just going to call these 1, 6, 11, and 16, which represents the beginning of their boundaries. Just for shorthand, because I don't feel like drawing out nodes. Which means that when we put them into, now we're like, oh, let's be fancy. Let's put these values into a binary search tree. So there's a bunch of valid binary search trees for this, but I could have like 6, 1, 11, 16, like this. Or if I initialize them, I could just have all of these be right pointers to start off. These are all right pointers. So it's basically a linked list. Okay? And so what I'm going to do is I'm going to read this weights file. So there's a file of weights and there's a file of like characters that represent those weights. So what I'm going to do is I'm going to scan the file, and suppose my file has like 14, 18, 2, 1, 5. 14 will get put into here. 18 will get put into here. 2 will get put into here, and 1 will get put into here, and 5 will also get put into here. Because that's where those weights belong. And then you're going to have the other file with the actual characters attached to them. So, let's look at the example. Project grades are more important than the Discord bot. It's true. I haven't had them that long. I just have to put them in Blackboard. And you say that now until you try to get help on the Discord bot. Like, project grade is what my project grade is. Okay. Any questions thus far? Tamor disagrees. It's something I'll work on this evening. The project grades. Again, it shouldn't be something I have to spend any amount of time on, but it is. And I will tell you guys, implying you can actually get help on Discord. It's better than nothing, I guess. Maybe there's maybe an argument to be made there. Okay, so now, what we're going to say is we have a binary search tree of ranges. So let's just say it looks like this. So I have 1, 6, 11, 16, like that. Okay. So now what we actually have inside of this is the BST that you implemented. Inside of each one of these nodes is a BST like pointer to a tree. So actually, if we like zoom out 16 here, after we fill this up, we might have something like 18, 17, 16, 19, 20. Like we have the actual little BST implementation inside of one of these S nodes. Okay? And so the S nodes are in what's called, it's a binary search tree, but it's also called a Splay tree, which we haven't gone over in class. We're going to go over now. The idea of a Splay tree is it doesn't balance really. What it does is whenever a node is accessed, it reconfigures the tree so that the node that was just accessed becomes the root. This is nice because if you're accessing the same node a bunch of times, then if it's the root, then you're there, right? So you get constant time, best case constant time access in a Splay tree, but worst case linear time access because the tree doesn't actually try to balance itself. You could have a Splay tree that is essentially a linked list. The idea though is if you're repeatedly accessing one node, its performance over an aggregation of actions will be quite good. And there's a proof to show that it is quite good, but we're not going over that. How do the characters work with the numbers given in Scrambled? Oh yeah, okay. So let me pull up Scrambled. Okay. The numbers in Scrambled, I was just making sure I was right before I completely talk out of my face. Let me switch to Chrome. All right, here are the weights. So this file is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, tall and a lot wide. Yeah. And so it looks like the highest value in here is 500 maybe? Oh no, 504, 510. Anyway, the weights from 1 to whatever the line width times the line height are all in here. And so what you do is you say, this is a scrambled image. Let me make it bigger. Do you want to make that node the node? Make that node the root before or after you insert. After an insert, the node that you just put a value into should be the new root of your splay tree. What we're saying is, if I sorted all of these out, this 1 here will be the top left pixel of my ASCII art, and if I go over to scrambled, that 1 is going to roughly correspond to maybe this 2. So what that is saying is, whatever character is associated with 2 needs to be at the upper left-hand corner of the unscrambled image. So the things in scrambled map to the things in weights. So what we're saying here, the fact that scrambled begins with 2 and weights begins with 286 means that the 286th pixel, if you scan like left to right, top to bottom, the 286th pixel will be whatever character is associated with 2. It's 34 wide and 15 tall, which gives us 510. Awesome. So, also if we find 510 in here, 510 and 1 are right next to each other. So they're just... So if you scan both of these files at the same time, like left to right, if you read one integer out of weights and one integer out of scrambled, you're going to be getting a weight character pair, which is what you programmed your binary search tree to deal with, which is integer character pairs. I'm going to pause a second in case there's any questions about that. I'm watching myself flailing, talking like this. Wait for myself to settle down. There I go. All right. Let's see if people are formulating questions. My hair is going to get longer and crazier as the semester goes on. We still have like 10 lectures or something? Okay, Time More gets it. Yes. Also, guys, it really helps if you, if I pause or whatever, if you guys put some thumbs up in chat, that lets me know that, it's kind of getting across. Because usually when I'm in the room, I can see you guys going, yeah, but I can't, I can't hear. Weights becomes keys. The weights file is telling you, basically what this file is saying is that the 286th pixel, if you read on scan lines, should be whatever is in the same position in the scrambled file. I think what Anwar is saying is correct. Oh, yeah. Weights becomes keys, pixels becomes values. Yes, that's 100% correct, now that I get that. In terms of your BST, the weights file becomes keys, the pixels file becomes values. Now what we could have done, go back to here. What we could have done is put everything into one big BST. We could have just put it all in ST with 510 elements in it, and then if we do an in-order traversal, we would get out the fixed image. And so when you're done reading them out, you do an in-order traversal of the S node tree and the BSTs inside of the S node tree. So each row is a new BST tree, and the Splay tree is a tree of... Yes. So scanner has S nodes inside of it, and there's a tree of S nodes that are organized. It's still a binary search tree, but it's a Splay tree. All right, Anwar gets it. So each row is a new BST tree. It's kind of similar to like what we were doing with AVL and red-black trees, but not. It's a Splay tree of BST trees, correct. It is a tree of trees. The weights correspond... No. What the weight means, that is the position... So if I read the first character out of scrambled and weights... So scrambled will give me like 1 or 2, because there's... For the supplied image that we give you, it's that like skull face, and there's just 2 different colors in that. So the first color is one character, and the second color is another character. What you get out of scrambled is what the character is in the final thing, and then when you pull another integer out of weights, it's saying... The weights is the position of that color in the original one. And then you read them out. Like you read them out as pairs. So weights gives you the key, as Anwar very succinctly put it. Weights gives you the keys for your binary search tree, and scrambled gives you the value, because when you build your scanner class, it's going to take a list of arguments that are the it's going to take a list of characters that are what you expect to find in the... or the characters that map with the numbers in the scrambled file. Whew! It is hard to talk about this. Doing int to char stuff? No. The weights... let me go back to... I have background music now. I'm going to go back to Chrome. I'm sure you guys won't complain if I go over time today talking about this. Oh, wait, this is scanner. Okay. You see how we have this ASCII art here? Or we have these 2 ASCII characters? Those are the characters. This is, if 1 shows up in scrambled, then it means use this ASCII character. And if 2 shows up in scrambled, it means use this ASCII character. That's what scrambled is. Then the weights file tells you what order to put the numbers of scrambled in to get the final picture. And you get this thing, which is actually like, if you open it up in a thing, it's like a winky skull, I think. Yeah, it's winky skull. All right, let's move on to Splay trees. Keep firing those questions, though. I'm happy to come back. All right. So how a Splay tree works is, let's have a tree. Let's say this is our Splay tree. Say we're accessing this one right here. Right? So the goal is to move this node that I'm accessing and move it all the way. all the way up to be the root, right? And so what we're going to do is we're going to perform a series of rotations. And you can also think of these as trinode restructurings, except your grandmama Z is always going to be your grandmama. Or like the highest node up there. So if you just have one parent, your grandmama is going to be your parent. And so it's like your grandmama Z is your grandparent, and what you're trying to do is you're trying to the resulting tree should be situated so that the node that you're doing the rotation on becomes the new root. So in an AVL trinode restructuring, we had like B, A, C at the end. Well, in the Splay, zig, and zag, you're going to have the node, we'll call it like X for marking the spot. X is going to be the new root, and then Y and Z are going to be children of it. Oh, it is Undertale. I knew I recognized that from somewhere. Am I having office hours today going on Discord? If I get my bot feature pushed in and I get grades in the Blackboard, then yeah, I'll do some office hours. It's not looking good for today, probably tomorrow. Are we supposed to be seeing Photoshop? We are. My gosh. I've been better about this. I've drawn all this stuff. I'm just going to start over instead of just talking to this. Alright, say we have this tree, and I've just accessed X. My goal is to make X the new root of this tree. So what I want to do is I want to do a series of rotations or restructurings such that with X's ancestors, so that X becomes the new root. So let me make sure I get my terminology about this right, because I always mess up. Zig, zig. So zig to the right, zag to the left. Or zig to the left. So we have zig. So we have a particular node. We have zig goes on the left, zag goes on the right. And so what we do is we look at our grandparent and we say this is a left and then a right. So this is a zig and a zag. And so then what we want is we just want to have X become the new root. So the way we do this is both of these values are less than this value. So this value is going to become, we'll make this Y and Z. So X will become the new, of this subtree, X will become the new root. Y is less than it, so it'll have Y here. And then Z is greater than it, so it will have Z here. So we'll be replacing this subtree with this subtree. And then we look up again, so now X is here. And so we're going to look up and we're going to have Z again. Stop hitting the button, Ben. Z. Oh, look, I have the little middle thing for Z. That's fun. All right, so we have X, Y, and Z again. Is this the same configuration? So again, we're going to have X up here, and then Y is going to be its left child again, and then Z and all of its junk is going to get moved down. Oh no, I hate this. Yes. Let's look at the examples on the course thing. Because this is so hard. This is a lot easier when you have like the physical board in front of you. Let's jingle. Okay. So we've accessed C, and we want to do a zig and a zig. So C is the lowest value here. So C is going to be the leftmost value, and then D will become its right child. And E will become D's right child because it's greater than both of them. What happens when you only have to move once? Then you just perform a zig or a zag. So you basically just do one little rotation. We'll see that here at the end. So now C is here. We've moved up, so here's our X again. And then we're looking at this node, B and F, right? Those are its parent and its grandparent. B is less than it, and F is greater than it. So F will become C's new right child. So we'll have C, F will become its new right child, and B will become its new left child. So C, F is now here, and B is there. And we do the same T0 through T3 thing. So this is T0, T1, T2, and T3. And so what we're doing is we're just creating a new subtree at our grandparent where C is now the root, and then we fill in the grandchildren. So T0 came here, T1 came here, T2 came here, and T3 came here. It's just like a trinode restructuring, except in the result, the thing you're trying to move up to the root has to be like the new root. Like the thing you're moving up has to be the new root when you're doing. So you used to have A, B, C, and this was based on key value for AVL trees. Now it could be, it has to be like either X, Y, or Z, or X, Y, or Z, or X, Y, or Z, and so on and so forth, depending on the relative values of the three things you're restructuring. How will you isolate what node is going to become the root for every zigzag to be done? Imbalance function? No. So the node that's going to be the new root is the one that we accessed, C. So we've just said, I access C. Like maybe you performed an insert on the line that C represents. Now you want to keep rotating the tree until C becomes the new root of the tree. So we started with this tree. This is our start. And we're ending with this tree down here. Whoops. I just still don't like it. Yeah, you have to... Yeah, you have to write a lot of cases out. And so then when... Still no questions? Okay. Also, by the way, get your BST done and really thoroughly tested before this. It's worth 70% of the project, whereas this part is only worth 30. So, like, and before you even try to do the splaying and all this other stuff, just make the tree and don't do any of the splaying and get your inputs and outputs working. Right? So, like, keep getting functionality incrementally working, save this nonsense for the last. Okay, so then at the end here, we're trying to get C on our quest to get C to be up to the root, to be the root. We have H, which is greater than it. So basically what we're going to do is we're going to rotate H down, and then C is going to come up. And so we're going to have T0, T1, and T2. And then we're going to rotate this up, and then we got T0, T1, and T2. Like that. Because you're only restructuring 2 nodes in that case. Okay. I'm gonna explain it again. I'm just gonna explain it again. Maybe the second time will work better. I don't know. Or maybe just hearing it explained like a different way again. For each zig and zag throughout the process until you reach the end, what becomes the new root after each zig and zag? The same node. So like, it's gonna be C because we accessed C. So this is always, we're trying to make this the root. So every zig and zag, every restructure that we do, C needs to become the root of that restructure. Yeah, the target node is another way to put it. And so we're going to be restructuring with our parent, because if we have to have a parent, otherwise we're the root and we're done, right? So as long as our target node has a parent, we're going to keep restructuring. So we're going to restructure with our parent, and if it exists, also our grandparent. And we're going to restructure in such a way that the target node becomes the new root between those 3 nodes. So we're going to restructure this because it includes C's parent and C's grandparent. And we're going to restructure it in such a way that the new root of this subtree is C. Okay, I'm pausing for questions. So we have we're restructuring 3 nodes, so we have 4 children. We're going to fill them in like we always do, T1 through T3, like this. And then we're gonna restructure, but in the result, we want C to be the root. So since C is less than D and E, D is going to be on the right of C, and E is going to be on the right of D. So now we see that we've sort of just flipped the order up. So C became the new root. Then we have T0 here, T1 here, T2 here, and T3 here. How do you know when you can stop restructuring? We're done when our target node, in this case C, becomes the root. Then we're done. We know we're almost done when C doesn't have a grandparent, because that means it's a child of the current root. Okay, so now, what 3 nodes am I going to restructure for this over here? What 3 nodes am I going to restructure on the second one? Okay, so the 3 nodes are going to be these 3. Which means that we're restructuring this entire subtree. But if these are the 3 nodes I'm restructuring, then A is T0. Oh shoot, who's down here? E. Oops. E. A is T0, This null pointer is T1, D is T2, and G is T3. C, B, and F. You guys got it. Yes. Some understanding is creeping through the interwebs. This is really hard to explain online. Okay. So now, let's look at B and F. So we know B is less than F. So if we put these in sorted order, so how do I put these three nodes in the sorted order, right? Who has the smallest value? Well, which one's on the left? It's B. Who has the middle value? Well, of C and F, F is greater because C went on the left of F. So it's like this, B, C, and F. Boom! Wait, no, B, C, and F is sorted order for these guys. So B, C, F is sorted order for those three nodes. We know that because it's how it be. No, we know that because B and C are left children of F, so it must be the largest node. And C is the right child of B, so C must be greater than B. When you're coding this, it's actually much easier just to sort the three values. It's kind of harder for us to visually look at this, but in your code, you can just sort B, C, and F. Also, these are in here this is a binary search tree of the alphabet, so they're also just in alphabetical order that way. So we have B, C, and F. And so then my question to you is, how do I make a subtree of the nodes B, C, and F that is still a valid binary search tree that has C as the root? How do I make a subtree? So these are three nodes here. How do I make a subtree out of just those three nodes where C is the root? So I could do this. C, B, F, right? C is the root. Right? Over here, when I had C, D, E, I could make C, D, E. And then the question is, how do I make a tree where C is the root? Well, I do that by doing C, D, E, which is what we got over here. Right? So you find the three nodes that you're going to restructure with, put them in sorted order, figure out how to construct a tree such that the thing that you want to get to the root is the new root, and then you fill T0 through T1 back in. So, T0 up here was A, so A is going to be over here. T1 was a null pointer, so this will be a null pointer. T2 was D, so D goes here. And then T3 was G, so G goes here. And if we look, I've just described this tree, right? So we got C, B, and... Would you set up a bunch of cases? Yeah, you could set up a bunch of cases. You could also just do a binary search insert on, like, you make C the root, and then you insert B and F onto that. Which is easier, probably, than doing a lot of cases. A lot of cases would work, though. Can you guys hear that background music? I don't even know where it's coming from. I think it's my neighbor. Oh, I do have to go at 3. Oh, I have a meeting. All right. I have a meeting at 3. But this is the most important thing I'm doing. Oh, but it's only 3 nodes. You don't have to do an insert. You do it another way. You can do a bunch of cases. You could say, here's the case when the one I want to be the root is the first element, second element, and third element. And then you'll be pretty much done. But you don't have to rebalance it. Well, yeah, you just have to do this damn splay operation. All right, so let's do this again. So we're doing C. I'm just going to explain it again. But hopefully things are starting to coalesce in your brain goop. So I'm going to be looking at my grandparents. And the goal is to make C the root. So that's our goal. So I look at these three values in sorted order, C, D, E, and then I figure out, well, how do I make a little subtree where C is the root? Well, I can take C, and then I insert D, and then I insert E. So I get this. So we're going to have our T0s, but they're all going to be null. So, and then that's what gets installed over here. Okay, so now C has moved up the tree. Congratulations, you're moving on up. Can you give a hint on how to possibly code this? It's annoying without parent pointers, but with if you had parent pointers, you'd have to maintain them, which is a give and take. So one way you're doing this is when you go to find C starting at H, you're going to track down through the tree like this. Right? So you can create a list of elements H, F, B, E, D, C like this. And then you can splay these. Then once you've splayed these, you can splay C and these two. And then once you've done that, you can splay H and C at the end. So you get 3 splays. So you just put these in a list on your way down, and then your splay will basically read the list backwards in 3 chunks until it's done. It would be so much easier with parent pointers. Kind of. Because the problem with parent pointers is you have to make sure that your inserts and everything like that and all this other stuff are maintaining your parent pointers correctly. And so it's another point of failure. But then you could turn around and say, isn't this crazy list that I'm going backwards through another point of... Yeah, it is. It sure is. But at least it's like a point of failure that's all consolidated. I would have done it with parent pointers. But I'm more comfortable with that. I'm more comfortable with that side of the trade-off. So that's how you would figure out the order of your splayings is... You're going to create a list of all the ancestors of your target node, and then you're going to perform the splay operation in the window of size 3 going backwards. So you take the target node and the 2 items before it, splay those, then we'll give you the target node again, then you take the 2 items before that, splay those, and then eventually you might only have 1 element, so you're just going to be splaying 2 things. As for the rest of it, like having to compute T0 through T3 is you look at the children of the nodes you're splaying. So over here we were splaying these guys. So you grab all the children of B, C, and F. You grab all of their children. So I grab this one, I grab this one, I grab this one, and I grab this one. Now notice that B and C are also children of B, C, and F, but you want to grab all the children that aren't B, C, and F. So they'll always be, in a splaying of 3, there'll be 4, and a splaying of 2, there'll be 3. Once you have those 4 things, you just put them in their sorted order. Whoops, that's a B. And that's how you get your T0 through 3. Oh, damn. Have an array to keep your nodes. Yeah, have an array to keep your nodes on the way down. You collect your T0 through T3 by going through the things that you're restructuring, grabbing all their children, and then putting them in sorted order. And then you perform the Splay operation. This is complicated. So again, implement it without the splaying. Just do like a normal binary search tree, get the scanner and the files read in and all that other stuff, and then get it to the point where all you need to do is put the splaying in, and then you can focus on that. And test as you go. Any other questions? I'm going to sit here and wait for questions for another 5 or so minutes. I have a meeting at 3. Jules, do you have any questions? No. So yeah. And in case you missed the announcements earlier, exam 2 will be take home. And on the 22nd, I think. It's actually pretty close to the final. It'll be covering a lot of material. It'll be significantly harder. That's just how it do be in this class. And then Project 1 grades are coming out either later today or tomorrow. And I'll probably be peeking into office hours tomorrow. Jules, do you want me to open that window?
Sounds like it.
You guys see this moron?
Oh my god, please fix that.
Jules. What a guy. Alright, I'm gonna check out YouTube's. Alright, guys. Alright, well, good luck. Ask questions in Discord. If you have general questions, you can put them in the general chat if they're just about what you're being asked to do and so on and so forth. Don't put any of your code in general chat because you don't want someone to take it and then we have to have an unfortunate meeting with you. And yeah, and we're trying to work, we're making the best of this very weird situation. Could I explain the weights.txt and scrambled.txt again? The weights are the keys for your binary search tree, and scrambled are the values for your binary search tree, like your BST. And then your scanner class is a BST of BSTs. And so you're going to go through weights and scrambled at the same time, character by character, so you get pairs. And then you're going to insert into your data structure whatever you found in weights, and then the value is going to be the character that maps to that value in the little character list that you supply to the constructor. And I'll take questions. If there's a bunch of prevailing questions, I will talk about them on Wednesday. Do remember that the penalties are waived, but Friday is the absolute final deadline. If it doesn't let you submit to the normal directory, you can submit to the late folders, and you won't get penalized for it. Okay, there will be 0 late penalty. As an acknowledgement of how weird things have gotten. I think I got it, kind of. All right, we're going to do it again. Do it again, since this is the question. So we have scrambled. 1 and 2, okay? Yeah. What does 1 mean? 1 means use this ASCII character, which is like sort of a grayed out face. And 2 means use this ASCII character. So, scrambled, these all map into those 2 ASCII values, right? Friday at 9, correct. 8:59. Then you're going to be reading. So I read 1 character at a time from this file, so that 1 value at a time. So I get 2 there, and then I go to weights, and I'm reading 1 value out of here. So I get 2 and 228. So what that means is I'm going to. If I look at the image, if I read the scan lines, if I count 1, 2, 3, 4, 5, 6, 7, 8, like that, when I get down to 286, that means I'm going to color 286 with this character. That's what having 2 in scrambled and 286 in weight means. Tuba's good people. Tuba's good people. I don't know, I think Tuba's more lovable than me, but opinion. Oh, we got an O! Yes! Cool. Ha ha! Excellent. Thwang. Ooh, got dog barks out of that. All right, guys. Are we good? All right. I've got to go to a meeting, but we'll talk more on Wednesday. Test as you go. Test as you go. If you're not even to this point yet, and you're this time, so make sure that your tests are good and they're complete. A testing seminar has been posted that was given by the TAs. I think you have an email from Dr. Marin on that. So there's a recording of it. Go look at that to learn how you can write better tests. We want you guys to write really good tests because we don't want... We want to make sure that you guys aren't just like hard-coding answers and things like that, so we give you different tests when we're actually grading your project. But we're not doing it to be tricky. We're doing it to make sure that people with not very flexible or robust answers are being graded appropriately. So learn how to write good tests. It's actually super important. What does the 228 represent exactly? If I have lines that are 10 wide, then I would expect 228 to be on the 22nd line in the 8th position, essentially. And that it would be that character. Now, that's not how it works for the actual example. It's like 15 lines that are something wide. I can't remember the number. But that's what the weight means. If I'm reading across the line, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, all the way down till I get to 228. The thing that's in scrambled is what color I painted, and the weight is how far down the image I counted in pixel order. For scanners, what am I supposed to insert for int ch? What you find in scrambled and weights. Can you give some ideas of what to test for BSTs? Put in large amounts of values. Put in values in ascending order and descending order in terms of weights. Put in scrambled values that are like randomly scrambled. But use a fixed seed, don't use time. You want it to be recreatable. So do a random scramble of values, but make sure that it generates the same random scramble so that you can debug it. I've made that mistake before where it does a completely different random scramble every time, and then I'll get a seg fault sometimes, which doesn't really help, right? So have it scramble up the numbers randomly, but like you can use a fixed seed so that it will always give you the same random scramble of like integers from 1 to 100. Because it's the insert order that will generate differently shaped trees. And what you want is you want to make sure that you're not memory leaking and seg faulting and that your tree is balancing correctly and you're not losing values. So if I put the numbers 1 to 100 in a wonky order, I should be able to in-order traverse that tree and get the numbers 1 to 100 back out again. If I'm missing 94, problems have occurred. We don't want that. All right, guys, I gotta go. But yeah, good luck. It's a hard project. But Project 3 is always hard. So yeah, and keep the questions coming on Discord. And have a nice day. It's beautiful out.